Greetings, everybody. My name is Richard Cromwell. Happy Pi Day from GoEngineer, and thank you for taking the time to join us today for Pie in the Sky, Exploring 3D Printing with SAF. Let's introduce ourselves here. My name is Richard Cromwell. I am a manufacturing applications engineer for GoEngineer based out of Metro Detroit. And today I'll be joined with by my friend and colleague, Simon Pinter.
How's it going?
There he is. And so our agenda today, our overall purpose is an in-depth look at Stratasys' SAF additive manufacturing technology and the workflows associated with creating parts on the H350. We would like to briefly introduce GoEngineer and Stratasys to help bring the scope of the solutions being provided into context. And then we will investigate SAF technology, how it works, and why it is such a powerful tool for manufacturers to be able to leverage. Then Simon will give a quick demonstration of the software and walk us through the typical workflow of running a build on the H350. We will then give you a preview of a future webinar topic that pertains to automating elements of post-processing, as well as what can be done with SAF parts once they are printed to further customize their appearance. And then if we have time, we'll do some Q&A. So up first, GoEngineer is the #1 worldwide technical resource for SolidWorks and Stratasys 3D printers. We support over 75,000 SolidWorks users, offer world-class technical training. We have over 220 certified technical experts on staff and over 60 offices spread throughout the entirety of North America. With more than 35 years of experience and tens of thousands of customers in high-tech, medical, machine design, energy, and other industries, GoEngineer provides best-in-class design solutions carefully selected that are easy to use, manage, and integrate with other platforms. Collaboration and partnership with our customers is at the center of everything that we do. So who is Stratasys and why is this important? Well, when you acquire a machine from Stratasys, you can rest assured that you have made a sound investment. Founded by Scott Crump, the inventor of fused deposition modeling back in the 80s, Stratasys is one of the oldest and most respected names in additive manufacturing. Stratasys has built their name based upon 30 years of experience in providing their cutting-edge technology to an unrivaled collection of devoted customers across several industrial sectors. And Stratasys is one of the original global leaders in applied additive technology solutions. Their aim today is to be the leader in polymer 3D printing through every step of a product's value chain. When much of the additive manufacturing industry it is presently enamored with metal additive, I thought it was awesome that Stratasys continues to focus on its strengths. This quote from Dr. Zeef, the CEO of Stratasys: "Our strategic objective is to be the first choice in polymer 3D printing, delivering the most innovative, highest quality additive manufacturing solutions for designers, engineers, and manufacturers of end-use parts." And I believe that they've really hit the mark. So in the recent years, Stratasys has dramatically increased their portfolio of polymer-based additive solutions. GoEngineer now offers a complete set of Stratasys solutions and an ecosystem to serve every part of the product value chain, from prototyping, manufacturing, tooling, production support, low volume, high performance parts, all the way through high volume part manufacturing. Stratasys is unique as they offer several different technologies, each providing the characteristics and materials optimized for each application, whether you're going for full color realism for prototyping and product development, all the way to mechanically accurate engineering prototypes, fast molds, strong metal-like replacement tools, jigs and fixtures, production parts for regulated industries like aerospace and medical with rigorous requirements. And then finally, what we're going to focus on today, fast and consistent parts for mass production. So what is SAF? And I'll start by kind of tying it into the whole Pi Day theme here. About 20 years ago, when my wife and I were first married, we were first living together, and I came home after working on a Saturday, and after walking through the front door, I went and put my keys on the counter, and then I turned to my right and looked into the kitchen, and it looked like a bomb had gone off in a bakery. There was flour and sugar everywhere, and dough and apple peels, and a tower of dirty dishes and pans and cooking implements and mixers and pages from cookbooks. It was just a disaster. And then I look into my living room, and my wife's on the couch, like all covered in flour, and she's like all passed out. And I go up to her, I'm like, "Are you okay?" Because I thought like the microwave exploded or something. And she's like, "I made a pie." And so she points at the counter, and there was this really kind of deformed apple pie. Now it tasted delicious, right? But it wasn't the best looking pie. Now, 20 years later, my wife is very, very good at making pies. She's like an expert pie maker, and she bakes pies with her daughters that not only taste fantastic, but they look like pieces of art. And the kitchen doesn't look like a war zone. So you're probably like, what does this have to do with 3D printing? And I'll show you. So that's a picture of me after my first time dosing reclaimed powder with fresh powder, and I look very similar to how my wife looked on the couch that day, completely covered in flour. But much like my wife's progression as a novice to experienced pie maker, with time and practice, advanced manufacturing processes like SAF can also be understood and mastered. So today, Simon and I are going to get you started along that path of understanding and mastery by showing you how you can use the H350 to create incredibly high quality parts from trusted materials with a clean and orchestrated workflow, all at production volume. So why additive manufacturing for production? Additive manufacturing provides a type of agility required to successfully navigate today's manufacturing environment. It can help in 5 critical business areas. So onshoring, the ability to move production closer to consumption and respond better to changes in demand. Flexibility to make one product on a machine one day and another the next, or to immediately improve a product by simply uploading a new CAD file. Additive brings speed, so you can start producing parts immediately instead of waiting weeks or months for retooling or shipping. And everybody knows that that's currently a big problem. Efficiency to produce low to mid volumes of critical parts less expensively. And then, of course, time to market. You can go from design to finished part ahead of the competition and far faster than was ever possible before. For those of you that aren't super familiar with additive manufacturing, there are actually 7 different families of additive manufacturing technologies. But before I talk about what differentiates SAF from other AM processes, I quickly want to mention what they all share in common. The process of any additive manufacturing technology can basically be divided into 4 steps. You have to create a digital 3D model, processing and slicing of the model in software, 3D printing of the product, and then AM technology material-specific post-processing, so removal of support, cleaning, post-curing. And then there can be a 5th step, which is secondary post-processing, like sanding, painting, media blasting, dyeing, etc. So here are the 7 categories or families of additive manufacturing. You have vat photopolymerization, stereolithography, and material extrusion, which is FDM. And then you have all these other ones, material jetting, which is like polyjet, binder jetting, which people don't use very much. And then there's powder bed fusion, directed energy deposition, which is more for metal, and sheet lamination, right? So these are the 4 technologies that are represented in the Stratasys AM portfolio. And then today, we're going to confine our discussion to powder bed fusion, which it finds its roots back in like 1988 with the development of selective laser sintering, and then it progresses to what some now consider the most advanced form of 3D printing, which is direct metal laser sintering. But SAF is a different branch on that tree because it incorporates elements of 2 other technologies, namely material jetting and binder jetting, as an alternative to using a laser as a source for fusion. So let me introduce you at this time to the Stratasys H350.
Accurate production-grade parts with best-in-class consistency. Print after print. Introducing the Stratasys H350. Manufacture consistent, functional parts at volume. Meet tough industry standards with industrial-grade components and superior quality materials. Powered by SAF technology with its unique thermal management and patented big wave powder deposition. the H350 provides part consistency build to build. Reproduce part qualities time after time, even on fine feature details and previously hard to print flat areas. Improve the quality assurance of your production with the flexibility to customize your workflow. Access powder management and build data to tailor part qualities to exact specifications. Modify your production process to suit your business, and even begin to explore certified applications for your parts. Reduce costs, not quality. Leverage the H350's high nesting density. Reuse unfused powder without compromising your next build. And lower your cost per part. Industrial grade print heads don't need frequent replacement, so you can maximize uptime whilst minimizing running costs. Plus, accurately predict fluid usage and avoid any unexpected costs. Predict spend and print your parts your way. Choose your workflow, grow your business, and stay competitive with the Stratasys H350.
So as you can see, the H-Series platform with SAF technology, it's built for throughput, it's built for reliability and repeatability, and then it does have economically compelling operation data. And with that, we're going to move forward and actually get into how does SAF work. So how does SAF technology work? This is a powder layer by layer additive manufacturing process in which parts are created by fusing selected areas of the powder a layer at a time. A layer of powder is deposited to recoat the previous, and parts are defined by jetting high absorption fluid into fine featured shapes with the industrial piezoelectric print heads. An infrared lamp passes immediately after, causing the powder particles to heat up and fuse together where the fluid has been printed. And what's great is they actually cure through each other, and you can see that here. It creates a very isotropic part. The unidirectional printing process is special to SAF technology and is designed to create a homogeneous thermal experience for all powder particles across the entire print bed. Uniform thermal processes reduce variability in the part manufacturing process, improving the consistency of the parts produced. So two key variables that need to be tightly controlled are therefore the powder recoating. And so this is repeatable, and the fluid jetting to ensure that only the required features are printed. SAF breaks new ground with its big wave powder management system, which I'll show you, and proven industrial grade piezoelectric print heads. But this little graphic is neat because it does show you how the calculations are done in terms of printing and then fusing and then recoating and then heating and then repeating that process over and over and over again. So the industrial grade print heads used in the H-Series are already proven in high temperature applications such as ceramic tile printing industry. They are designed to be robust but still print fine feature details repeatably in a tough and challenging manufacturing environment. I had the video pause here for a reason, and you can see these channels that are in the print head. Unlike many other powder bed fusion systems for the H350, these proven heads are not a consumable item. So you don't need to worry about them in terms of total cost of ownership when you're looking at the machine. Stratasys includes required replacements as part of your service contract. And so these channels are one of the key features of these heads. So these industrial grade print heads are constantly recirculating the HAF, or the high absorption fluid, which we're going to talk about in a second. But the recirculation allows the fusing agent to be kept at a constant temperature and pressure, which are two important factors in jetting the material consistently. Another advantage of SAF technology that makes it superior to a lot of the other older powder bed fusion technologies is that SAF only requires one fusion agent, HAF, to be jetted via the print heads to mark the areas of the part we would like fused via the infrared lamp. So for example, with other powder bed fusion technologies, two agents are required, one for marking the area of the part they intend to fuse, the other for delineating the outer perimeter of the part where fusion needs to stop. This method not only uses more consumables, but can lead to undesirable surface defects in the part. The primary active chemical constituent in HAF fluid is carbon black, as a suspension in petroleum distillate liquid base. So this is another advantage in SAF's favor because other powder bed fusion and detailing agents are water-based. So the difference in pigment saturation between the two is akin to that in oil and water paints. So the half fluid combined with the industrial print heads are two of the critical differentiators in terms of SAF's like techno-evolutionary superiority over legacy print head-based powder bed fusion systems. The big wave powder management delivers consistency of powder recoating and has a unique powder recirculation system to reduce powder and thermal aging. This is a whole area of study, like the whole recoating of powder bed systems and for that matter, stereolithography and all additive manufacturing. That's a critical component of having successful prints and good quality surfaces. And so the big wave powder management is excellent at providing you with that really even layer, but at the same time, it's taking any surplus powder and then recycling it. And so this helps you obviously in maintaining, because the powder is already heated up, so it's a thermal thing, but it's also a consumables thing. You're using less powder than you'd find in other systems. So overall, SAF technology empowers customers with industrial grade technology, giving production level throughput for end use parts. SAF is different from other 3D printing and powder-based fusion technologies due to the strong differentiated assets. Very quickly, I'll just cover the materials. There's only two of them right now. We have a high yield PA11 nylon and SAF PA12, which is another nylon. PA11 is 100% bio-based from sustainable castor oil. And the SAF PA12, which is really what you see a lot of other powder bed fusion systems printing with, we also brought that to market and made it available on this machine as well. And it's great for high nesting density and really fast turnaround. So finally, we're going to talk about, well, why should we even care about SAF? What separates this from other additive manufacturing technologies like FDM, polyjet, and stereolithography, and what are some good application examples? So one of the big advantages here, and this goes for the new like classification of additive manufacturing technologies that are more production-based, okay? So beyond being able to produce highly detailed, accurate parts at high volume, you are able to utilize you can actually build your and prototypes on the same platform that you're going to use for mass production of the parts. And so you can develop prototypes with the same strength and accuracy and ductility as you would find in your final part. And so this gives you the ability to get your products to market faster and at less cost. Some key industries and applications in the automotive space, people are using these machines already for sensor housing, HVAC grills, vents, ducts, cup holders, cable clips, covers, and bridge manufacturing to keep their line running, actually. Industrial machine components, we talked to somebody today about printing end-of-arm tooling using the H350, which I think is a great application. Impellers, brackets. One of the big benefits of this technology is it's supportless, right? You don't need all these additional support structures like you do in FDM and in stereolithography or DLP. It uses the unfused powder itself to support the parts as it's being printed. And so you can really leverage that in your designs and create some pretty fantastic parts and add them all to the build really, really quickly. And so it's one thing for me to say how awesome SAF technology is, but let's take a listen to what the folks at Roush Performance have to say.
We develop vehicles for our customers, from Mustangs to F-150s that suit their lifestyle. On the F-150 project, we had a late design change that we had to pivot very quickly on. We had to reposition the front camera on the trucks, and in doing so, the solution that we came up with and thought, hey, we can mock this up and try it, actually ended up being our production solution for the program.
The reason we went with 3D printing is because of the time issue we had. We leveraged our existing relationship with Stratasys, and that's where they introduced us to the SAF technology on the H350. The advantage to using this technology was we could get our prototype parts as well as some PPAP parts potentially in the same build, and that supports our production volumes.
The impact of using the SAF technology on the H350 was tremendous to Roush. We were able to greatly reduce our time to market by going with this manufacturing method.
All right, so again, consistency over large production runs, flexibility and ease of use, and an improved business case over a lot of the other additive technologies and even, traditional manufacturing methodologies out there. So with that, I'm going to turn it over to my friend and colleague, Simon, to give a demonstration of the software behind the H350.
Thank you, Richard. We'll see if I can actually figure out how to use this go-to. Bear with me. All right, I think you can see my screen, yeah?
Not yet.
Not yet. Okay.
But that could just be me. There we go.
Perfect. Okay. So Richard, thank you for teeing that up. I got the easy part of this presentation. I get to show you the software. And I am assuming, like almost everyone else in the world, love an easy button. So I'm going to show you how GrabCAD Print works in unison with the H350 for build prep, sending your jobs over to the machine and getting everything up and running. So if you are not familiar with GrabCAD Print, this is the software that kind of covers nearly the entire ecosystem of Stratasys 3D printers, from FDM to PolyJet to DLP and now H350 SAF. It's really a drag and drop, change a couple of button settings to get builds prepped, but I will go so far, and for anyone who's familiar with the extruded thermoplastic process, FDM, on this call, I'm going to go so far as to say H350 build prep is easier. I said it, you heard it here first. So I'm going to go through the process. As Richard was saying, one of the huge benefits of the H350 or SAF process is that we can take quite a few, well, not that one, we can take quite a few different files. And instead of thinking about a build volume as an X and a Y table onto which you'll lay your parts out, we've got a three-dimensional volume that we can fill. And that's what really facilitates the high throughput production. So in GrabCAD, we can load our parts up. It's going to give us a warning if there are any issues with our meshes. And GrabCAD does a really great job of telling us if there are issues and repairing them really, really rapidly. Looks like one of my parts is in the wrong unit, so I'm just going to grab it real quick here, and I am going to make it a little bit bigger. Okay, perfect. So this is a nice number of parts. They'd fit great on an FDM platform, but we're going to go hard, right? We're going to make some duplicates. And let's just duplicate everything 249 times. Now I got a heck of a lot of parts. And what on earth am I going to do to get this build prepped so that they all fit within my build volume? I'm just going to zoom out enough that we can see the breadth of everything that's about to go into the build, but I'm going to just do a Control-A to select everything. And really the only settings that I'm going to be interacting with are all under this 3D Nest tab. Like I said, I love an easy button, and for 99.9999% of builds that I've ever sent on an H350, everything under this automatic tab is more than enough to set the build up optimally. I'm going to lay out a couple of scenarios. Number one, setting a nesting height. SAF technology, the only thing that determines print time is going to be your Z-axis. It doesn't matter how many parts are in your build. It's all a matter of how tall your build is. So there could be a scenario where, let's say, you work an 8-hour day, as we do in this office, maybe a little closer to 9 hours. But I know that I want to do an H350 build that is going to start after I do a breakout in the morning And I want to be able to turn the machine over to do an overnight build as well. So I need to tell the machine, print, but I only want you to print as long as it takes so that the machine will be done in time before I leave. So if I set a nesting height, I'll go ahead and just say, let's make that height 3 inches. The software will then calculate how long that print's going to take about 6 hours. And I'm going to hit Start Nest. So this is where the fun is actually happening in the background. We get to watch it while the computer is doing the hard work. And we'll zoom in here. And as it's thinking, you can see on the right-hand side, it's calculating, okay, this is how many parts we've been able to fit. This is how tall the nest is, and this is the density of parts in that nest. Just gonna hit stop. I think we're at a good point. It's gonna stop the nesting process. And I'll look overhead. I'm just gonna clean up our workspace so we can see a little bit more about what's going on. Speed up the processing as well. Anything outside of the build volume won't print. And for whatever, there we go. Okay. So here is a representation of the build volume at a 3-inch height, which is going to take 6 hours. So that's scenario number 1. Let's say we want to run a print overnight. I'm going to get rid of the set nesting height option, reselect my parts, start the nest. It's going to do the same thing, but at this point, it's going to take advantage of that entire build volume. And like I said, I love an easy button. I'm letting the algorithm do all the work for us. So I'll stop that nest. And by the way, the longer I let it go, the more densely it's going to be able to pack those parts. That's what the processing time really takes into account. Is it's evaluating all the different part geometries, and it's trying its best to fit as many parts into that build volume as possible. So I am going to clean up our workspace a little bit, and we can talk about the next scenario. So I've got just these two. Go ahead and repair those parts. Perfect. And we'll make a couple of copies. Awesome. So bringing this window back out. So we talked about a scenario where we want to run a day build. And we're going to set the nesting height to a particular height so that we know that the print is going to be done before we leave for the day. What we haven't really touched on yet is the sustainability of the system, or rather the efficiency of material usage of the system. With the H350, we can get away with reusing up to 70% of the powder in a build for the next build. We just have to add 30% of unused powder into that mixture. The golden rule with the H350 for a steady state of printing is going to be a 12 to 15% nesting density. That means at the end of a print, when we break our parts out, there's going to be just enough powder so that all we'll have to do is add 30% fresh powder, and we're not going to be accumulating any powder on the back end. So if we know that that's a rule, we can specify a density. I'm just going to keep it at 12%, and I'm going to tell the nest to start. So we're still using that whole build volume because I haven't put in a nesting height, but I have specified keep processing until you get up to 12%. All right, so it gave us 0.055 more than I told it to, but I think we'll give it a pass on that one. And then the final thing that we can use as a stop criteria is going to be time. Now, this isn't print time. This is processing time. If I want to start this process of nesting, get up, get some coffee, go to lunch, which I don't do very often, either of those things. But let's say there was a scenario where I did. I can set my stop time at an hour, and I'm going to let my computer just keep crunching and develop the most efficient packing of parts within that build volume. I'll spare you all that. And we'll just do a quick nest for the next thing I want to show you. We can stop it there. We can do better than this, obviously, but for the sake of demo, I'm just going to zoom in. We talked about how easy it is to nest. One of the things that might be giving you anxiety on this call right now is like, I'm a service bureau, or I'm the central printing hub of our company, and we're going to see 250 different kinds of parts every day. My operator is going to lose track of what belongs to whom, and parts are going to get lost in the process. It's kind of hard to keep track of that kind of stuff. Well, what you can do is tell your designer, hey, go back, open up every single one of your CAD files, put a little label on it so that when it comes out, we'll know to whom it needs to go. I guess that's one way to do it. But like I said, I love an easy button. And in GrabCAD, I can right click on a face of a part. I can add a label to a body. Rotate that. You guys are gonna love this. AMUG is coming up soon here, so like we have to do one of these, obviously. We've got a couple other settings that we can go through, either embossing, debossing, change the size of the text, change the extrusion or debossing distance. Hit save. It'll prompt you to update the geometry. And it literally tosses that geometry right onto your part. So now when I've got 300 different parts coming out of a build, it's very easy at a glance to determine to whom that part needs to go. And presumably you'll pick a face that isn't one of your A-class surfaces, something internal that'll be unobtrusive. Last thing I'll point out when we're talking about nesting is part orientation. In SAF technology, your best best looking surface from an aesthetic standpoint is going to be anything that is downward facing. So I know that I want my A-class surface to be downward facing. Okay, but when I hit the nest button, the issue that we run into is that the software is going to choose whatever orientation works, but I know that I want my A-class surface to be downward facing. So we'll call this my A-class surface. Yep. If I know that I want this to be downward facing and I don't want the software to really screw around with how it's oriented, under the orientation tab, I can orient a face to a plane. Did the wrong one. That one. Perfect. And I can tell the software, make the pack, feel free to rotate the part however you want, but only about a particular axis. So if I tell it lock that Z axis, it actually means you can move the part however you want, but it can only rotate about the Z. So in this scenario, we can duplicate a couple of these. Let's just call it 10, great. And I'll go ahead and nest. And we'll get rid of the height. I don't want to look like I'm cheating here. And I didn't select this part, so it didn't get added to the nest, but you get a sense of how this works. It's going to make the parts fit however you have defined that they are able to rotate. And at this point, again, love an easy button. All I'm going to do is I'm going to hit print, and it literally will take me longer to walk down to the printer and press print on the user interface than it did to get the build set up. So with that, Richard, I'm going to pass this back over to you.
All right, can you see my screen?
I gotcha.
All right, so now is a good time for us to go through the workflow. So I'll get that started.
Yep, and I'm gonna let Richard pressed the button on this one, but I'm going to walk through what we're doing here. And this is the process of what you're going to do when you walk up to the machine in the morning when it's time to unload a print. So here the operator, my colleague Colin Manchester, he's putting a build box on top of a completed build on the user interface. He's telling the machine to raise that build up into the build box, and he's pulling it out onto his handy dandy cart because it's a little heavy and I've got scrawny arms. It's hard for me to move things like that around. So Colin is cleaning up the interior of the machine. We're able to reuse a lot of that powder. And we're just making sure that all the surfaces are clear of the loose PA11 powder. Here's an image of how you dose the machine with powder once you have mixed in your 30% fresh. We're gonna add our half fluid. And now we get to break our parts out. So taking that build box over to the Farsoon, which is part of this process, this is the machine that's actually gonna take the majority of our, I was gonna call it waste powder, but our used powder, and reclaim it for us. So there's a vibratory table, and once Colin starts breaking these parts out, powder is gonna fall down through that sieve, hit the vibratory table, and it's going to take that reclaimed powder, put it into a blue jug for us, and get it ready for next time. We get to play Indiana Jones, do the whole archaeology dig, pull our parts out. Depending on the density of parts, sometimes that powder will just fall away. It looks like the movie may have frozen. Now, there we go. So pulling those parts out, breaking off as much powder as we can. Richard's gonna talk about some automated post-processing machines here in a couple of moments, but you'll see Colin is gonna take those parts, and for now in our facility, while we're waiting for our dimension machines to get installed, he's taking them over to a shot blast cabinet, blasting off the last of that powder that is stuck to the nooks and crannies of the part. And at that point, they're good to hand over. Some of the key features of the machine, everybody loves tech specs. Layer thickness, 100 microns, maximum print time under 10 hours, which is pretty amazing. There is some cool down time involved as well, but you can remove a build from the machine for that cool down time. So it's not taking any time away from the next run. If you needed to know that the machine was 1,800 pounds, that's how big it is. We talked about the materials that are currently available, which are going to be PA11 and PA12. We use that half high absorption fluid for binding the powder together. For build prep, I told you I love the easy button, but you can also use build processors like Materialize Magics for build prep as well. Certain granular, and the pun was intentional, certain granular functionalities can be accessed, Richard loved it. Certain granular functionalities can be accessed in some of those other softwares, but I want a big red button that I can press and say that was easy. I love this about the warranty. You know, it's like everything else you buy. The warranty is for 1 year and then you get a service contract, but included in that warranty or that service contract are the print heads. That's a really big deal because these are of the most, I don't want to say complicated, but of the most integral parts of the machine. And it's not something that you want to have to worry about replacing on your own. And it's not something that needs to be replaced by you. What we haven't pointed out yet is these print heads were actually developed to print directly onto ceramic tile. The technology does not physically contact the surface onto which it's emitting a fluid. So the print heads stay real clean for a really long time. Some of the site requirements that you'll want to keep in mind, pretty standard for an office environment or for a standard manufacturing environment. Things like air extraction are important to keep in mind, and relative humidity is pretty crucial for the printing process as well. Here in the Detroit office, we sometimes struggle with being able to maintain the 40 to 55%. So we've got some humidifiers that do a great job of keeping the room up to spec. And a couple of power requirements that you'll want to keep in mind as well, but we've got all this documentation that we'll happily and readily hand out to you. So Richard, back to you.
Yeah, sure. So just a couple other things. You can see here that we do have a lot of solutions for the post processing. Once the machine is done printing, you have different build boxes, you have removal carts, you have the powder retrieval station, and that's all fantastic because it gets you a really nice part. But the last thing that we're going to talk about today, it's a little bit of a preview for what we'd like to be able to talk about next time, and that is, what do you do with these parts once they're printed? As you can see, when Colin was working with those parts and manually cleaning them, that's a very labor-intensive way of doing things. And if you're cranking out thousands and thousands of parts, nobody wants to do that. And so we have a solution that goes along with the SAF technology, which is dimension post-processing equipment. You have a machine that allows you to be able to essentially dump all your parts in there, and then it will rotate it and blast it with air and clean everything off, so you don't have to do it manually. I just cleaned 275 PA11 dog bones manually. It took me about 3.5 hours. This machine could probably do it in about 6 minutes. Yep. The PowerShot S, okay, is another thing that we can add to the mix. This is a smoothing station. It allows you to improve the surface finish potentially of the part. And then there's the DM60. All of these parts can be dyed a huge rainbow of colors. And so all of these are relatively hands-free processes. They're very quick, and it's a great way to be able to customize your parts for your customers. And another thing to consider, and the reason why we kind of got to talk about this in another webinar, is this is actually a pretty deep topic, and there's different machines for vapor smoothing as opposed to the PowerShot, and all, the dyeing processes and different equipment specific to each of those. So I just wanted to kind of show you that there's multiple options in terms of workflows to get different types of customized parts. And I know we went a little bit over. If anybody has any questions, please, you can type them into the Q&A. We're not going to take anybody's time today in terms of that, because we can just answer them via email. However, unless there's anything pressing, I didn't see anything in the chat. So it looks good. Yep. Okay, well, thank you so much, everybody, for taking the time to join Simon and I and learn more about the H350. Don't forget to go to our YouTube channel. We have over 100,000 YouTube subscribers. Please feel free to like and subscribe, and that way you can stay tuned for the next iteration of the sequel of this webinar, which is going to go into even more depth, because this machine is super deep. It's super powerful. And I'm really excited that Simon and I were able to share this information with you guys. So thanks so much, and we will see you next time.
Thanks, everybody.